There is nothing more important in physics than the speed of light. Its abbreviation, c, literally means constant, like the constant, the one that matters. But here's a secret. The speed of light changes all the time. It's about 25% slower in water, 35% in glass, and more than twice as slow when traveling through a diamond. C itself measures the speed of light in a vacuum, about 300 million meters per second, and it's literally the fastest anything in the universe can go. And you know what? In nature, light is always fast, because 25% slower than the fastest thing in the universe is still stupid fast. But in the lab, scientists have done something extraordinary. Created beams of light that are slower than a car. And then, with the literal flick of a switch, they can freeze that beam in place. If you're thinking, that sounds tricky, you're right. But if scientists can master it, this could be the key to our computing future. The key to catching a beam of light is called electromagnetically induced transparency, and it was first observed in 1991. It's a way of taking something opaque and making it perfectly transparent at a given wavelength using nothing but a couple beams of light, which weirdly enough, is possible. To do it, you need an opaque cloud of gas, say sodium gas, that's super cold, so atoms aren't moving very much. That cloud also needs to be in a vacuum, so there's no outside interference. And the atoms in the cloud need to have electrons with 3 available energy levels. Initially, the electrons in each atom are in the lowest energy level. Then you shine a pair of lasers into the gas. The first is called the probe, and it emits light with just the right amount of energy to take electrons from the first energy level to the third. If you were to shine it into the cloud by itself, it would all get instantly absorbed by the electrons jumping up to that third energy level, so the cloud would stay opaque, because being opaque just means you don't let light through. Now, there's another laser called the coupling beam, and it has the right amount of energy to take electrons from the second energy level to the third. Except, if all the electrons are in the lowest energy level, there aren't any to move from level 2 to 3, so the beam just passes through untouched. So if you shine the light separately, only the coupling beam goes through the cloud. But when you shine the two beams together, things get weird. If you turn the coupling beam on first, and then the probe beam, the probe can suddenly shine straight through. What happens is, the coupling beam is trying to shift the electrons from level 2 to 3, but at the same time, the probe beam is trying to shift them from 1 to 3. Faced with these two tugs, the electron basically gets trapped between them, effectively ending up in level 1 and level 2 at the same time. And when that happens, the electron doesn't absorb photons from either beam of light. Physicists call this situation a dark state, which sounds ominous, but it just means that the electron ends up in the dark about the presence of either laser. Now that the light's not getting absorbed, the cloud becomes transparent to the laser, and the probe beam can travel straight through. It's a neat trick, but it doesn't come for free. The probe can pass through, but it does so super slowly. See, the probe beam is made up of a bunch of light waves at frequencies that are really similar, but not quite the same. As they enter the cloud, those waves slow down at different rates and start to interfere with each other. And that causes the entire probe beam to slow down. Like, instead of traveling at 1 billion kilometers an hour, it's suddenly going more like 25, slow enough that you could keep up with this beam of light on a bike. That sudden slowdown also bunches up the light beam into a tiny, sluggish package. But physicists weren't done once they'd slowed light to a crawl. In some cases, they went on to stop light altogether. They accomplished that by turning off the coupling beam while that scrunched up package of light was making its way through the gas. At that point, the package completely vanished. Once again, the energy in that light got absorbed into the sodium atoms. But what's incredible is that that light wasn't just gone. When they turned the coupling beam back on, a package of light emerged with the same exact phase and energy as it had before. Somehow, the sodium atoms were storing information about that beam of light. So far, scientists have been able to freeze light for up to 1.5 seconds. But it's not just for kicks. This might also have applications in fields like quantum computing and cryptography. For instance, the last time you bought a computer, one of the specs you probably had to pick was the amount of memory or RAM that you wanted. The ability to store something for later is kind of a fundamental part of what makes computers useful. But the quantum computers built so far don't really have memory. Since quantum information is more complex than ones and zeros, these machines can't store information like a regular computer does. Electromagnetically induced transparency seems to offer one way to solve that problem. After all, stopping light is all about getting atoms to hold on to information in the configuration of their electrons, and that's exactly the stuff quantum computers are working with. Now, having a lab's worth of equipment keeping a bunch of sodium atoms near absolute zero doesn't sound scalable, But there are other ways to induce transparency. Some researchers have done it using materials much closer to room temperature, and in 2005, IBM developed a computer chip that could slow light by a factor of 300. That's a far cry from the 30 million times slowdown done using ultra-cold atoms, and it's not the same as stopping light, but it's a step. And even if it's all a long way from being useful, there's definitely still something incredible about taking one of physics' most important rules and bending it to our will. Thanks for watching this episode of SciShow, and a special thanks to our patrons on Patreon who make it possible for us to make videos like this. If you want to join the amazing community that keeps SciShow going, you can find out more at patreon.com/SciShow.